In Lesson 8.6, the ratio and root test, we will explore the two titular tests and find that they actually both have the same conditions and same conclusions. And who knows, if we're lucky, maybe they'll even make some sense along the way. So that being said, let's go ahead and explore the ratio test first and see how easy this test actually is. Recall from previous chapters that we have said that if the next term in a sequence is less than the magnitude of the current term in the sequence, then all the terms are, therefore getting smaller and smaller. And as we learned in the alternating series lesson, we call that absolute convergence. Again, looking at the magnitude of the next term compared to the current term. Well, the way we wrote that previously is we would say that the magnitude of the next term had to be less than or equal to the magnitude of the current term. And if that worked, there was our absolute convergence. We're going to formalize that a little bit better using the ratio test. And in the ratio test, what we're going to do is look at the limit as n approaches infinity. So we're going to look at all of these terms in the long run. And what we're going to do is create a ratio of each next term to each current term. Now, before I give the conclusion here, I want you to consider what would happen if each of the next terms is less than each of the current terms. What would happen to this ratio that I've presented to you right here? Well, clearly if each term is getting smaller, then as n approaches infinity, this must be less than 1. After all, if it's equal to 1, then each term is the same as the current term. And if it's greater than 1, then the terms are actually getting larger. So if the terms are getting smaller, then we have that the magnitude of this ratio must be less than 1. In fact, I've already told you how to tell if this is diverging. We're going to use the same type of test. We're going to, again, look at the next term compared to the current term. But if that is greater than 1, that means the terms are growing, and certainly the series is going to diverge. Now, what happens if the limit as n approaches infinity? What happens if this equals 1? And let me go ahead and write this formally here. If this equals 1, then we actually cannot draw any conclusion at all. This would be an inconclusive case right here. And if that happens, we'll just stop and say, well, we'll need to use another test in order to make a conclusion. So, all that being said, why don't we take a look at 4 examples of series using the ratio test. So, here's our first example that we're going to use to try to find the convergence or divergence using a ratio test. In this series right here, I hope that it's painfully obvious to see that our current term in the series is simply going to be n cubed over 2 to the n, while our next term in the series, a sub n plus 1, is just going to be n plus 1 cubed over 2 to the power of n plus 1. Now, in order to use the ratio test, all I need is to look at the limit as n approaches infinity of the magnitude of the ratio of the next term over the current term. Let me show you how ugly this is going to look, and then we'll clean it up a little bit, and we'll actually figure out a way to not ever have it look this ugly again. So, there is my next term in the sequence, and over our current term in the sequence. This is a hideous complex fraction here that, quite honestly, I just don't want to deal with. And so what we're going to do is, just as you learned in elementary school, we're going to go ahead and multiply by the reciprocal. And in fact, in the future, for all of the examples that are coming up, I'm simply going to write them in this form. There is my next term multiplied by the reciprocal of my current term. I just wanted to do it this way first so that you could see where this is coming from. But all the rest of the examples, I'm just going to start this way. So if we go ahead and simplify this a little bit, the limit as n approaches infinity. Let's see, over here I'm going to have n plus 1 cubed. And on the bottom, I will have n cubed. So that will simplify those. Those aren't really going to simplify too much. But if I look at 2 to the n power on top, and 2 to the n plus 1 power on bottom, I'll see that I actually have one more 2 on the bottom than I do on the top. Plug in any value for n that you like, and you'll see that this is the case. So I'm just going to go ahead and multiply times 2 on the bottom. Now, as n approaches infinity, I hope you can tell that this n plus 1 cubed that I have on top and this n cubed that I have on the bottom are essentially going to cancel each other out. For large values of n plus 1 cubed and n cubed are essentially the same. So if I do cancel those out, what I'm going to end up with here is simply 1/2. Now, what do we know about 1/2? Well, what we can say is by the ratio test, we end up with 1/2, which clearly is less than 1. And so our final conclusion we can make is that this particular series is going to converge. Each next term is less than each current term in terms of magnitude, and so by the ratio test, this series will converge. Well, if that makes sense, let's go ahead and take a look at another example of a series using the ratio test. And so, here's another example of a series that we're going to try to determine the convergence or divergence of using the ratio test. If we do this, I'm going to skip the step where we define the current and next terms. I'll leave that as an exercise to you. But if we want to find the ratio of these, we'll do the limit as n approaches infinity. The magnitude of the next term, which will be n plus 1 to the n plus 1 power, divided by n plus 1 factorial. So there is my next term. And again, just like in my last example, I'm going to multiply this by the reciprocal of the current term. So I'll end up with some nasty ratio that looks kind of like this. Well, if I clean this up a little bit, do some simplifications and all that, let's see what would happen here. If I have n plus 1 to the n plus 1 power, and then I have n to the n power on bottom, there's no way I can really simplify those at all. And so let me just go ahead and write those out. N plus 1 to the n plus 1 power on top, and on bottom, n to the n power. So we'll see what that does us here in just a moment. But if we take a look at these two other parts of this ratio, that and that, hopefully you can tell that n factorial is n times n minus 1 times n minus 2 times n minus 3, etc. Where on the bottom we have n plus 1. That's n plus 1 times n minus 1, n minus 2, and so on and so on. So if we go ahead and simplify those, all we're going to be left with is actually just n plus 1 on the bottom. That n plus 1 follows by n factorial, which will cancel the n factorial on top, and we end up with this here. Now the question is, what's going to happen to this as n approaches infinity? My answer is, before we get to that, I think we can simplify this just a little bit more. Notice that we have a whole bunch of n plus 1s floating around here. What's going to happen to this term here in the numerator and this term in the denominator if I were to expand and write all this out? Hopefully you can tell that what would happen is I would end up with n plus 1 to the n power divided by n to the n power. So you could call this n plus 1 to the first power here if you so chose. And when you subtract those, the ones would go away, and you can see that this is what I would be left with. So what is the value of this ratio as n approaches infinity? Well, if you take a look at it, again, n plus 1 to the nth power versus n to the nth power are essentially the same thing, and what I'm going to end up with here is simply 1. So since my ratio test resulted in 1, what is my final conclusion? Well, by the ratio test, I end up with 1, which equals 1. And so this test is inconclusive. And I am going to be very specific about this. This test is inconclusive. This doesn't actually tell us anything about the series itself. In fact, if you use our original test for divergence all the way back at the beginning of the chapter, the nth term test for divergence, as we called it, I think you would find that this series actually does diverge. So it's not that the series is inconclusive. The series does one or the other. But the ratio test itself was inconclusive for this series. So I hope that gives you an idea of what an inconclusive test would result in. Let's take a look at two more examples of our ratio test. For our third example, we're actually going to take a look at a series that we're already familiar with and see if the ratio test gives us the same conclusion as we would have come up with using our prior knowledge. If you take a look here, you will probably realize that this is actually a p-series. And of course, we remember the rules about p-series, in that the value of p is what's important here. If that p is greater than 1, we will converge. And that if p is less than or equal to 1, we will diverge. Let's see if we get the same results using a ratio test here. Now, of course, to use the ratio test, I'm going to do the limit as n approaches infinity, and I'm going to do just as I've been doing. Here will be our next term. That will be 1 over n plus 1 to the p power, and I'll multiply that by the reciprocal of our current term. So we have something that looks like that. Now, if I go ahead and simplify this quite a bit, which of course I'm going to have to do here, well, this is interesting. I have a n to the p on top. I have n plus 1 to the p on bottom. Recall that those are, as n approaches infinity, essentially the same thing. And so this will approach 1, telling me what? That the ratio test is actually, once again, inconclusive for this series. Now, does that make sense? I mean, we have our guidelines written here on the left side, and we know that this isn't inconclusive. We know that it either converges or diverges. But what I challenge you to do is to think about the value of p. Think about the value of p. If p is greater than 1, then the denominator will be greater than the numerator, and this actually will be less than 1 then as a ratio. Likewise, if p is less than 1, then the denominator will actually be less than the numerator, and so this will escape to infinity somewhere, and it will diverge. And of course, if it equals 1, then we have other issues to deal with. But this does give you an example of how the ratio test can be used to prove things that we already know about other series. Well, our next example won't be quite so easy, but let's go ahead and take a look at it anyhow. So, our last example for our first set of these notes is a monster. It looks terrible. However, if you break it down, you can see that clearly this is an alternating series. We have this negative 1 to the power of n minus 1, and that's going to keep this series bouncing back and forth between positive and negative. You can see that it does have a ratio involved here, 3/2 to the n power. Now, that doesn't necessarily make it a geometric series, but it does have some ratio in effect. And then we have n squared on the bottom. So let's see where all this takes us. It looks like we could use the alternate series test, but let's use the ratio test and just see what happens. So if we do that, we're going to have the limit as n approaches infinity. And again, this is a magnitude, so we don't need the negative 1 to any power involved here. But let's go ahead and take a look at our next term in the sequence, which will be 3/2 to the n plus 1 divided by n plus 1 squared. There is our next term in the sequence. Now, let's go ahead and multiply by the reciprocal of the current term in the sequence, that is n squared over 3/2 to the n. And once we simplify this, hopefully we'll be able to draw some conclusion about this series from the ratio test. So let's go ahead and do that here. Let's start with our 3/2 to the n plus 1, which we have in the numerator, and our 3/2 to the n, which we have in our denominator. I will posit that these two terms will simplify. In fact, sure, we have one more 3/2 on the top than we do on the bottom. So that's going to leave us with 3/2 on the top. Now, the n squared and the n plus 1 squared, there's not a whole lot we can do with that. Of course, we'll talk about as n gets significantly large what's going to happen here, but for now, they don't algebraically simplify at all. Alright, but now let's go ahead and talk about it. As n does approach infinity, what's going to happen to the n squared in the numerator and the n plus 1 squared in the denominator? well, they're both going to cancel each other out. They're going to become uh, so close to each other that they become irrelevant. And look what we're left with here, 3/2. What do we know about 3/2 relative to this ratio test? We do know that 3/2 is greater than 1, and based on that, let's go ahead and draw our conclusion. What we're going to say is by the ratio test, we can go ahead and say 3/2 is greater than 1. So this series does in fact diverge. We are able to draw a conclusion using our ratio test, and our conclusion is that this series will explode off to infinity somewhere or another, and certainly will not converge to a single value. So now that we've explored one absolutely convergent, one divergent, and two inconclusive examples of the ratio test, let's go ahead and take a look at the root test, which has the same conditions and the same conclusions as the ratio test, and that'll make it very easy for us to deal with. So, what exactly is the root test? I said earlier that it carries the same conditions and the same conclusions as the ratio test. And here's what I mean by that. We use the root test when we find a series in which all the terms of the sequence are raised to some exponent. Of course, the root is the inverse of the exponent, and so we'll use that to cancel the exponent out, essentially. And then we'll determine if the series underneath the exponent itself is growing or shrinking, and that'll tell us a lot about the terms and therefore about the series itself. So let me show you what this means here. If we have some given series, what we're going to do to figure out if the series is absolutely convergent is we'll take the limit as n approaches infinity, and we'll take the nth root of the magnitude of the current term. Now, we'll look at that, and as I said, if that ends up being less than 1, then we can say that the terms are getting smaller and smaller and smaller, and therefore that the series will converge absolutely. Now, we'll say that the series diverges, on the other hand, and you'll notice that this is very similar to the ratio test. If the nth root of the magnitude of the current series is greater than 1, and that includes if the nth root of the magnitude actually goes off to infinity. If that's the case, we'll consider infinity to be greater than 1. So in that case, it diverges. Now, just like with the ratio test, you might be asking, what happens if the root test yields a value of 1? And let me go ahead and write that here. If the limit as n approaches infinity of the nth root of the magnitude of the current term, if all of that equals 1, then the root test will in fact be inconclusive. And notice there are so many similarities between the root test and the ratio test that all you need to remember is one set of conditions, one set of conclusions, and it makes it that simple. So, because it is that easy, let's just take a look at two examples here and see the root test in action. For our first example of a root test problem, we're going to go ahead and take a look at this series that I've presented you right here. And all we're simply going to do, just like with the ratio test, is we're going to take the limit as n approaches infinity, although for the root test we're going to do the nth root of the current term, which in this case is essentially just rewriting the term here. So it'll look like that. And if I do a little bit of simplification here, you can probably see what's going to happen. But just in case you don't see it, the root that we have right here and the exponent that we have right here are essentially going to cancel each other out. And I will be left with the magnitude 2n over n plus 1. This should have been a magnitude in here. I was getting a little lazy, I suppose. But if we look at that, the limit as n approaches infinity of 2n over n plus 1, what does that equal? Well, you can take the coefficient of the, or the leading coefficients rather, if you like, or you can do L'Hopital since it goes to infinity over infinity. However you want to go about it, it will equal 2. 2 clearly is greater than 1, and so what we can say is that by the root test, what we end up with is 2, which is greater than 1. So this series clearly diverges. Now, I want you to take a look at one more thing before we move to our last example. If you considered this a sort of geometric series, we have a, and this would be r to the n. Consider what kind of conclusion we would make using the geometric series test. Of course, this ratio is a variable ratio, but think about it as n approaches infinity, and consider what conclusion you would make for a geometric series test versus the conclusion that we did make for a root test. Hopefully you see that everything is starting to come together quite beautifully. Let's take a look at one more example here before the end of this lesson. So, for our final example on this lesson, I begin by challenging you to, once again, pause this video, work out example F on your own, and then come on back. Once you do, hopefully what you'll see is that this series, just like the last one, could be done in a different way. But let's go ahead and use the root test, since that's what we're supposed to be learning about right now. So if I go ahead and do that here, it'll be the nth root of e to the negative n power. That's a pretty easy simplification, just as I feel that example e was as well. The nth root will of course cancel out the nth power, and all we'll be left with here is just e to the negative 1. And what's the limit of e to the negative 1 as n approaches infinity? Well, of course, that's just e to the negative 1. Now the question is, what do we know about e to the negative 1? And I'll tell you what we do know is that that is less than 1. If you want to think about this as 1 over e, maybe it'll be easier to tell why that's less than 1. But either way, what we can conclude here is by the root test, we do end up with 1 over e, which is less than 1. So this particular series here converges. In fact, because it's the magnitude we were looking at, right? The magnitude, remember? Because it's the magnitude we were looking at, this actually converges absolutely. So that's a beautiful thing right there. Now, once again, if I were to rewrite this problem as the sum from n equals 0 to infinity of, let's say, 1 times 1 over e to the n power, hopefully you could look at that and realize that this is actually another example of a geometric series. Again, the ratio is less than 1, and again, we make the same conclusion that we did with the root test. It's quite beautiful when that happens, when we can solve a series convergence-divergence problem more than one way. A lot of times that won't be the case, but when it is, it's great to see the interplay of all these tests. And of course, in a situation like this, so long as you follow the directions, it's your choice in how to do it. So, we've covered a lot here. The ratio test and the root test, although very similar, accomplish their goals in different ways. One looks at the value of the next term compared to the value, or rather the magnitude of the current term. And of course, if that's growing, then we have a divergence series. If it's shrinking, we have a convergence series. That's all the ratio test. And then in the root test, we found a way where we could actually, in a manner of speaking, get rid of the exponent and just look at the terms of the sequence. So consider all this, and good luck on your 8.6 assignment.